Good afternoon, dear students. This is Khadar handling JEE and NEET classes of V4U. Today I came forward. We have to discuss about the second part of chemical bonding. In previous session we discussed about introduction, Lewis and Coastal symbols and octet rule we discussed. Next one, types of the bonding also we discussed, ionic, covalent, and coordination covalent bond, hydrogen bonding and its characteristics, everything we discussed. Now in this session I am going to discuss the important theories of in chemical bonding, that is valence bond theory, hybridization, Vsepr theory and molecular orbital theories. Next important concept, formal charge, how to calculate the formal charge and what is Fazan's rule, and finally bond characteristics, that is bond order, bond length, bond energy and bond angle. Now let us start with here theories in chemical bonding. The first theory is VBT, valence bond theory. Now I am not going that much detail about this one, because with respect to competitive exams we are going to discuss here. Valence bond theory. In this valence bond theory, main what is the type of orbitals are involving here, overlapping of atomic orbitals is involved. Now in this overlapping of atomic orbitals, if it involve, then we can main discuss here two types of bonds we are discussing. One is comes under here sigma bond and second one is comes under here pi bond. How the overlapping of atomic orbitals takes place if it sigma bond is there, is how the atomic orbitals will overlap whenever the pi bond is forming. Here the sigma bond is there, the overlapping of atomic orbitals. For example, if we consider here atom A, which is combined with here one more atom here. Now how these two atoms are combined, overlapping takes place here. This is overlapping of atomic orbitals. This overlapping, it is called here end-end overlapping. Now end-end overlapping is nothing but like this. The end-end overlapping takes place between the two atomic orbitals. It leads to formation of the sigma bond. Now how about the pi bond here? For example, if you take it here, I am taking here one pi orbital, this one p orbital. Next one I am taking one more p orbital here. If these two p orbitals are closer to each other, then I am writing here like this. This is called as here end-end overlapping, and this is called as here sidewise overlapping. Whenever the sidewise overlapping is there, it leads to the formation of pi bond. That is the main important concept. Already studied this one, sigma bonded. Sigma bond is a strong bond, and as well as this is the first bond which is formed between the any of the two atoms. That's why the sigma bond, it is here the strong bond. Sigma bond is the strong bond, and as well as here the sigma bond is independent existence. It won't depends on others. Now sigma bond is the first bond which is formed between any of the two atoms. Next one, it is less reactive. For example, if you want to break the bonds between the two carbon atoms, then we have to supply large amount of energy. That's why it is comes under here less reactive. Next one, come to the here pi bond. Pi bond, it is generally we have to consider it is weak bond, and it is dependent on sigma bond. Whenever the sigma bond, after forming the sigma bond only, the pi bond will be forming along with the sigma bond. That's why it is known as here dependent bond. It is completely depends on sigma bond. Next one, it is more reactive. You might have been observed in the organic chemistry, in electrophilic addition reactions. For example, if you take it here, C double bond C here, if you want to add, for example, I am adding here HBr, then this is called as a addition reaction, electrophilic addition. If I am take it here, for example, if you then immediately here H plus, this is the Br minus, the negative part, first the H plus will be coming and attacking here, the double bond will be shifting. When check here also bond is there, here also bond is there. Now this bond is called as a sigma bond, and this bond is called as a pi bond. Pi bond is more reactive. Whenever the any reagent will come and attack the pi bond will be shifting first, the sigma bond will not be shifting, so that it will form here one addition product. Such as here, if you take it here, this is the minus, it will form here H, and this is Br. This is the way addition reaction will take place, and this is more reactive. more reactive in nature. Next one here, some overlappings are there. Okay, now SS overlapping is there, SP overlapping is there, PP overlapping, and PD overlappings are there. SS overlapping, generally sigma bond, what is the overlapping will take place here? SS overlapping, SP overlapping, and PP overlapping will take place. Okay, generally pi bond, even in PP overlapping, pi bond also will be forming. Okay, next one, what are the example for the SS overlapping? You can take H2 molecule, here SP, okay, HCl molecule you can take it here, you can PP overlapping, you can take F2Cl2 Br, you can take it here, you can take it here, some okay D block elements you can take it. Okay, this is the way. Okay, now here sigma and as well as pi bonds will be forming through here different types of here overlapping of atomic orbitals. Okay, now next one, the extended the form of okay this valence bond theory, that is very important concept for the competitive exam, that is called as here hybridization. Hybridization, it is a very important concept, dear students. Okay, in organic chemistry also we have to identify what is the hybridization, okay, of the particular carbon, what is the okay, if it is single bond is there, what is the hybridization, if it double bond is there, what is the hybridization, if it triple bond is there, what is hybridization. Sir, first of all, what is meant by here hybridization? It is the process of intermixing of two or more atomic orbitals with a slightly energy difference and to the formation of new set of hybrid orbitals with the equivalent energy and geometry. That is known as here hybridization. Okay, nowadays we are observing okay hybrid fruits in our market. Okay, if you take it here, different vegetables and different fruits. Okay, it is okay everything which is comes under process here hybridization. That fruits is called as hybrid fruits here. Since we are using here orbitals, that okay is why it is called as here hybrid orbitals. Hybrid orbitals. Here the electrons will not be involved in the bond formation, only orbitals can involve. Here okay, hybrid orbitals, whenever the hybrid orbitals are forming here, it leads to the formation of sigma bond. These hybrid orbitals can't form here any type of pi bond formation. This way it is a sigma bond formation. Next one here, types is there, very important types. Okay, next one, the first types, what are the SP is there, next one Sp2 hybridization, Sp3 and Sp3D or DSP3 you can take it here, or Sp3 D2 and finally Sp3 D3. This is the types of the hybridization that we are going to discuss here. Okay, now Sp hybridization, it is the intermixing of one s orbital and one p orbital to forming two hybrid orbitals okay with equivalent energy. That's why it is known as here Sp hybrid orbital. For example, if you sometimes asking in the competitive exam also, what is the percentage of S and P character in particular hybrid orbitals? For example, if you check it, one example I am teaching, the rest of the things you can easily do it. Percentage of S is equal to okay number of S orbital here 1 divided by total number of orbitals 2, okay, percentage 100. Okay, that's why here 50% is there, already written percentage, no, okay, 50. Next one here, percentage of P, you can take it here 1 by 2 into same here 100, that is 50. Okay, 50 here 100. If you take it here Sp2 also here 1 by 3 into 100, that is 90. Okay, that is 33.33% will come here. If you take it here 2 by 3, that is into 100, 66.6. Here S character is 25%, so that you can follow the rest of the hybrid orbitals too. Okay, next one, what are the examples will comes under here Sp. Sir, any shortcut formula is there, sir, to identify easily okay a particular hybridization of the particular molecule or compound or any ion. Now I am going to a very important formula. If you are using that formula, whatever the molecule or compound, you can easily do it. Now I am giving the formula for hybridization, and our books also different formulas are there. Now I am giving the only one formula. Okay, now you can take it here. Hybridization is equal to okay group number or number of valence electrons of central atom plus a number of mono atoms is divided by 2. By using this formula you can calculate anything. Okay, the group number or number of valence electrons of central atom plus number of mono atoms is divided by 2. This is a very important formula to calculate this one. Okay, let me take it here. Okay, now I am starting with here Sp hybridization. Sp can take it here, CO2 molecule is there. Next one BeCl2 is there, next one HCN is there, next one ethine. Okay, C2H2. Sir, I will consider this molecule, sir, whether this formula is correct or not. Okay, let me check it here. CO2 I am calculating. Okay, hybridization. Okay, which is the central atom here? Carbon is the central. Okay, now group number. Okay, sir, we don't know, sir, group number. Okay, that's why I gave number of valence electrons. What is the number of valence electrons central atom here? 4 plus number of mono atoms here. Okay, what is mono atoms here? Okay, those atoms having the valency which is equal to 1, that is called as here number of mono atoms, such as hydrogen and as well as all halogen atoms, which is comes under monovalent atoms. Monovalent atoms. Okay, now let me take it here. Is oxygen comes under monovalent or divalent? Very good. It is divalent. That's why I am considering is 0 by 2. That is equal to 2. 2 means here S and P. 1 S orbital, 1 P orbital, total 2. Okay, now this formula is correct or not? You can take it here BeCl2 also. Check it here. 2 plus. Okay, chlorine is monoatom. Comes under halogens by 2, that is equal to, that is sp hybridization. Okay, let me start with here sp2. There are how many s orbitals? Okay, sp2 hybrid orbitals 3. Okay, example for this one here. Okay, bf3. Okay, or bcl3. Okay, next one, this is here sp hybridization alkynes, already written here. Next one here alkenes generally. Okay, next one SO2, SO3 and so on, etc. And very important, graphite which is comes under sp2 hybridization, which you studied in P block in from class 11th. Okay, now let me take it here bf3, whether it is comes under or not. Check it here. 3 okay, valence electrons plus number of mono atoms 3 divided by 2, that is equal to 3, that means here sp2 hybridization. Okay, now you can apply for the remaining compounds also. Here also check 6 valence electrons plus 0, 6 by 2. 3, here also 6 plus 0 by 2, that is equal to 3. Okay, this is. Next one comes to here sp3 hybridization. Total how many hybrid orbitals? 3 plus 1, 4. Okay, next one example for this one here, very important. Okay, CH4, CCl4, next one NH3, H2O. Okay, next one SiCl4, very important here, diamond. Okay, next one here graphite only wrote. Now one more, allotropes of the carbon is that is called as here Buckminster fullerene. Already we know, we studied in class 10th, that is C60. Okay, buckyballs. Okay, discovered by H.W. Croto and R.E. Smalley. Okay, here diamond and so on, etc. All alkanes also comes under okay sp3 hybridization. Now let me take it here CH4 if it comes under sp3 or sp2. Check it here. Carbon 4 valence electrons plus number of hydro monoatoms 2, that is equal to 4 means here sp3 hybridization. Okay, now whenever sir, what about here angle sir, and what about here its geometry sir? If sp hybridization is there, general without having the any lone pair of electron, its geometry is linear. And what about its okay, then bond angle sir 180 degrees. Sir, okay, how can you identify sir here bond angle? Now let me take it here C double bond O. If you take it here, what is the angle my dear students here? 180 degrees. If you take it the BeCl2 also, the bond angle is 180 degrees. Sir, what about here sp2 hybridization geometry and as well as this one? sp2 hybridization geometry is trigonal planar also we can call. Next one, what about this bond angle my dear students here? 120. For example, imagine this is the boron atom. Okay, fluorine, here also fluorine, here also fluorine. Now okay, just have check it my dear students. What is the bond angle over here? The bond angle between atoms, okay, bonds. Next, what is 120 degrees. Next one, if it okay sp3 hybridization is there, what about shape or else? Okay, next one bond angle. Okay, now geometry first of all here without having the any lone pairs. If the lone pairs is there, one more theory is coming ready to okay explain, that is valential electron pair repulsion theory. Okay, geometry it is comes under tetrahedral. Okay, next one, what about bond angle is 109 degrees 28 minutes. Sir, what about here geometry sir? You can take it here hydrogen, here hydrogen, here hydrogen, here hydrogen. Now let me take it, is it comes under tetrahedral or not? Check it here. This is all atoms which is bonded with carbon in different corners. Okay, now if you take it here angle, its angle is 109 degrees 28 minutes. Okay, this is the very important. Next one comes to the higher Okay, next one is Sp3d. Sp3d total how many hybrid orbitals? There are 5 Sp3 hybrid orbitals are forming. Example for this Sp3 hybrid orbitals is, okay, now first of all you can take it here, PCl5, okay, next one SF4 you can consider, ClF3 you can consider, okay, next one Xc, F2 and so on, etc. Now let me take it here. Sir, what about general without having any lone pairs? Geometry is trigonal bipyramidal. Its geometry is, okay, sir, any bond angles will be, sir? Yes, bond angle also is there. The bond angle here 90 degrees and 120 degrees. This is the bond angles. Okay, whenever Sp3 hybridization is there, but condition without having the any lone pairs. That's why here 5 bond pairs and as well as 0 lone pairs. Here 4 bond pairs, 0 lone pairs. Here 3 bond pairs, 0 lone pairs. Here 2 bond pairs, 0 lone pairs. That lone pairs as well as bond pairs, if you understand, you can easily predict the geometry of any molecule. Okay, now let me take it here one example, PCl5. PCl5 if you take it here, phosphorus is the central atom. Okay, whether it is comes under Sp3 or not, check. 5 plus number of more atoms 5, 5 plus 5 by 2, that is 5. 5 means Sp3d. Okay, let me take it here, Cl, here Cl, here Cl. Okay, now I am connecting the here bonds. What about this one, my dear students? This is PCl3, but what is my shape? Okay, my molecule PCl5, here Cl, here Cl. Very important in CBSE, this is the PCl5 molecule. Okay, there are 3 equatorial bonds are there. Very important, and one of the, okay, JEE question, this is how many equatorial and how many, okay, axial bonds is present in PCl5. There are, this is comes under equatorial bonds, how many? 3. Next one, what about axial bonds here? Okay, one is the top of the axis, next one is bottom of the axis, that is called as here 2Cl, that is called as here axial bonds. The ratio of, okay, equivalent and axial bonds is equal to, okay, 3:2, very important. Okay, next one more. Question also is given from the JEE, this one. If you heat this PCl5 molecule, how it will be convert? If you heat this molecule, okay, now there are 5 chlorine atoms are there. Out of 5 chlorine atoms, which chlorine atom is going to break? Just check. Those atoms which is bonded away from the center atom, which is away here. This is everything is equal distance. Okay, now what about here? This is the one top of the plane, one is the bottom of the plane. It is due to more repulsions, it is away from the central atom. If you apply heat, then what will form, my dear students, here? Okay, now PCl5 gives rise to apply heat, PCl3 and chlorine gas is releasing. Okay, what bonds are breaking? This bond and as well as this bond will be broken. Then it is forming here PCl3, phosphorus trichloride. Okay, now this is about here this one, and very important, okay, we can discuss in SFO, okay, in valence bond theory, sorry, Vsepr theory. Next comes under here Sp3d2, very important here. How many okay, the Sp3d2 hybrid orbitals? There are 6 Sp3d2 hybrid orbitals will be formed. Can you give the example here? Yes, SF6 is there, you can take it, and BrF5 and Xc, F4 and so on, etc. Okay, let me take it here. Whether it is comes under this hybridization or not, check it here. I am writing directly. 6 plus 6 divided by 2, that is equal to 6. Here also 7 plus 5 divided by 2, that is equal to 6. Here number of valence electrons of atom here 8 plus 4 divided by 2, that is equal to, everything is comes under 6 Sp3 hybrid orbitals. But okay, here only comes under, okay, 6 okay, bond pairs are there and 0 lone pairs. And now I did not introduce any type of lone pairs now, because lone pairs if there, then geometry of the molecule will be different, explained by valence shell electron pair repulsion theory. Now this is there. What is the geometry of the molecule? That is called as here octahedral. If the octahedral geometry is there, sir, then what about here? Bond angle is 90 degrees. Now let me, sir, what is the shape of this octahedral, sir? Let me take it here. Here fluorine atom, here fluorine, here fluorine. Okay, now let me take it here. This is the geometry of okay, Sp3d2, that is especially comes under SF6 sulfur hexafluoride. This is the called as here octahedral. The bond angle between the two atoms, if you take it here, 90 degrees. This is the very important, dear students, please note down. And come to the last one is Sp3d3. Sp3d3 total number of hybrid orbitals is equal to here 7. Okay, Next one, what are the examples will comes under, sir? Here, that means here IF7, okay, and as well as here XC, F6 and so on, etc. If you take it here, what about geometry of this one, IF7? IF7 geometry is pentagonal bipyramidal is a, okay, geometry. Pentagonal bipyramidal. Next one, what about bond angles, sir? General bond angle here I am taking here 72 degree and as well as here 90 degree we are taking as a bond angle. Show me this, sir, what is the pentagonal, how the geometry will be like this. Now let me take it here. Iodine atom here I am drawing here, okay, fluorine, okay. Now fluorine, IF7. Now check it here. This is only IF5 only. Then remaining 2 more fluorine atoms are there. Let me write here. This is F and this is F. Okay, this is geometry is pentagonal bipyramidal. Okay, this is a very important concept which you studied, okay, in class 11th about hybridization. Okay, this is the number of bond pairs. How much is equal here? Number of bond pairs is 7 and as well as number of, okay, lone pairs is equal to 0. This is the very important concept in, okay, entire this one. Okay, dear students, please note down. Then after we can start with here Vsepr theory. Thank you. Okay, dear students, okay, so far we studied about hybridization and the different types, what is the number of bond pairs, lone pairs, and what is the characters of S, everything we studied. Now let us go to next very important theory, that is called as here Vsepr theory, valential electron pair repulsion theory. Okay, what this explains? That means here, if any molecule or any compound, if it contain, okay, some lone pair of electrons. Sir, if it lone pair of electrons is present in the central atom, then what is the effect of that molecule? If it does it affect of the molecule and its shape and as well as bond angle? Yes. Okay, that due to the presence of that lone pair of electron, okay, it will change the geometry of the molecule and as well as this bond angle. How it will be here? Here on scientist is given, okay, the repulsions, okay, order between the lone pairs and as well as bond pairs. Lone pair repulsion, which is much more greater than that of lone pair, bond pair, which is greater than that of bond pair. This is the order. Okay, very important. Don't forget, dear students. Lone pair. Next, lone pair, bond pair. Next one, bond pair repulsions is there. Okay, next one. If we consider some molecules here, those atoms, okay, are those molecules or compounds which contain lone pair of electrons. Now let me start here with the NH3 molecule, if we consider NH3 molecule generally, okay, valence electrons, okay, atomic number 7, configuration 1s2, 2s2, 2p3, if we check it here, 2s 2 electrons and 2p there are 3 electrons. Okay, now what I said here, only these orbitals only can form, involve in the bond formation, and paired electrons doesn't involve in bond formation. Then okay, if we take it here, how many lone pairs you can, I am writing the electron dot structure here, 1 2 3 4 5. Okay, that means 3 bond pairs, and as well as here 1 lone pair is there. Now let me take it here, hydrogen, like this. If you take this molecule, okay, now hydrogen is there, here also hydrogen, here also hydrogen, then what about okay, number of valence electrons surround of nitrogen atom is equal to 8 here, 2 4 6 8. Now this nitrogen got octet configuration. Here what will happen here, okay, hydrogen also gets okay, helium configuration. This is the NH3 molecule. Now due to the, now let me draw the correct okay, geometry of this one, H and as well as H. There are how many bond pairs here? There are 3 bond pairs. How many lone pairs here? 1 lone pair is there. Now let me take it, what is the hybridization here? 5, number of valence electrons of central atom, 5 plus 3 by 2, that is equal to 4. 4 means what is the hybridization? Sp3. Okay, so far we discussed there is no lone pair of electron. If lone pair is there, then what is the geometry and as well as here bond angle of the particular molecule. Next one, Sp3 hybridization is there. There is 1 lone pair. This shape is called as here pyramidal shape. Okay, now due to the presence of this lone pair of electron, this is a very important concept. Due to the presence of this lone pair of electron, there is a repulsion between the lone pair of electron versus bond pair. Here lone pair is not there. Here what is the condition will apply here? Lone pair bond pair, because here lone pair, here bond pair, and bond pair, BP, that only. Okay, now okay, generally without lone pairs, okay, generally Sp3 hybridization is there, that is okay, tetrahedral shape and 109 degrees 28 minutes. But due to the presence of this one lone pair of electron, okay, now the molecule has been distorted from tetrahedral to okay, pyramidal shape. There without having the lone pair, 109 degrees 28 minutes of the CH4 molecule or CCl4. Okay, now if you take it here, 107 degrees. That means bond angle also reduced and molecule also has been distorted due to the presence of lone pair. Next one comes to the here H2O molecule. Same here also I am writing directly. There are 2 lone pair of electrons here. Next one, 1 hydrogen here, 1 hydrogen. How many lone pairs, dear students, here? Here 1, here 1. Total lone pair of electrons here 2. There are 2 lone pairs and as well as here 2 bond pairs. Okay, hybridization which is comes under 8. Number of valence electrons 6 plus 2 by 2, that is equal to what? 4 Sp3. Sp3. Okay, 1 lone pair is there, that is okay, pyramidal shape. 2 lone pairs is there, that is called as here V shape or bent or angular shape. This is very important. They will ask in a competitive exam, okay, which of the following molecules should contain 2 lone pairs and 2 bond pairs. Okay, then we have to identify the molecule. Next one, if they are asking like this here, okay, in particular molecule, okay, having the 2 lone pairs and bond pairs, identify the molecule and what is the geometry. Geometry is V shape or bent or angular shape. This is the very important, dear students. Next one comes under here SF4 molecule. SF4 generally there are 6 valence electrons is there. Out of 6, how many participate, dear students? 4. That means 6 minus 4, you can easily identify, that is 1 lone pair. Next one, how many bond pairs is there? There are 4 bond pairs. Okay, now come to the hybridization. 6 plus 4 by 2, that is equal to 5. 5 means here Sp3D. Sp3D means already you know, okay, that is trigonal bipyramidal, but due to the presence of a lone pair of electron here, what is the shape of this SF4? Here fluorine, here fluorine, here fluorine, here fluorine, here fluorine, and I am writing the lone pair of electron here like this. Then what is the geometry? Just you have to identify. What is the geometry, dear students, here? Okay, this is we can with the help of this is we can cut the wood particles, okay, wood pieces also. What is this one? It is called as here seesaw shape. Seesaw, SF4. Okay, if you take it here ClF3 also, ClF3, okay, in that ClF3 there are 7 valence electrons, 7, okay, okay, how many bonded here? 3. 7 minus 3 is equal to 4. 4 means how many bond pairs? Okay, here lone pairs is equal to 2, next one bond pairs is equal to here 3. Okay, ClF3 if there, then what is the geometry of this one here? Cl, here F, here F and lone pair of electrons is present. How many lone pairs here? There are 2 lone pairs. Okay, sir, generally we have to write that is like this we can write, no sir, this is okay, Cl F F F. Okay, we should not write directly T shape. Okay, well, we have to write bent T shape. Sir, why we have to write the bent, the word bent? That means, okay, due to the presence of the 2 lone pair of electrons, here lone pair repulsions will be very more when compared to lone pair versus bond pair and BP versus BP, so that the molecule has been distorted from trigonal bipyramidal to bent T shape. This is very important. Next one comes under here. Okay, XeF2. XeF2 generally 8 valence electrons, 8 minus 2. Okay, 6 means here there are 3 lone pair of electrons and 2 bond pairs is there. Then if you take it here Xe, then I am writing here fluorine here, I am writing fluorine. Okay, I am taking 3 lone pair of electrons. Here 3 lone pairs, here 3 lone pairs. This is generally we can call it is distorted, okay, trigonal bipyramidal, but okay, if you check it that completely structure, this is linear geometry. Okay, XeF2 is the linear geometry like this. Okay, what is there? Because a lone pair of electrons mainly which disturb geometry and as well as bond angle between the 2 atoms in a molecular compound. Like that many compounds is there. This is about what, my dears, here. Okay, Vsepr theory which is completely explained about the geometry and this, okay, and okay, shape of the molecule. Next comes under here very important theory, that is called as here molecular orbital theory, very important. MOT, this MOT theory, okay, and so much discussion also there, many points are there. Then with respect to competitive level exam only I am going now. Okay, molecular orbital theory. Molecular orbital theory, here also same orbitals only involved here. Okay, but not electrons here. Now we are having the generally 2 types of okay, orbitals. One is comes under here bonding orbitals, and next one here anti-bonding orbitals. Okay, in that bonding orbitals generally we have to represent here with NB, anti-bonding orbitals represented with generally here Na. Okay, this is the very important. Okay, now with the help of this one, what you are going to calculate molecular orbital theory for okay, homo and as well as hetero atomic molecules. Homo and as well as here hetero atomic molecules, we are calculating here what is the bond order. Okay, what is the bond order between the atoms here? Okay, for homo molecules also there and hetero molecules also there, we can calculate here what is the bond order and what about its bond length, what about its bond dissociation energy, and what about its stability order, and what about its bond strength. This one I am going to give the complete shortcuts here based on that. Very important for the competitive. Number of questions will be asking from the NEET and as well as JEE here. Let me take it here homo atomic molecule. Okay, before that one small information here NB and as well as here okay, Na. This bond generally bonding orbitals are having the lesser energy when compared to here anti-bonding orbitals. Okay, just anti-bonding orbital generally we have to represent with here star. Here representation is like okay, before we can write here sigma and as well as here pi, okay, and sigma star and as well as pi star, we are representing the orbitals here. Without stars it is called as here bonding orbital, with star sigma star, pi star, like that is there, that is called here anti-bonding orbital. Okay, obviously bonding orbitals will be having the lesser energy when compared to anti-bonding. Okay, now first of all what are the points you are going to study here? We are calculating about here bond order. Bond order generally we can discuss in the bond characteristics here, half into NB minus Na. Okay, now just minus it indicates here, just I am defining minus means here difference, half. The half of the difference between bonding orbital to the anti-bonding orbital is known as here bond order. Okay, NB and as well as Na. Next one very important. Okay, next one, if what about the stability here? Stability. Okay, if NB which is greater than Na, that molecule will be more stable. If NB which is less than Na, the molecule will be unstable. What about sir, for NB is equal to Na, molecule doesn't exist. Molecule doesn't exist, such as okay, He2 molecule, Ne2 molecule, all noble gaseous elements. Okay, it is generally it is called as inert gases. It doesn't react with other elements at a normal condition except okay, xenon. Xenon will be forming the number of compounds at higher temperature and pressure, that is the separate. Okay, this is next one comes under here. I am giving the entire points here. Bond order, whenever you want to calculate bond order, they will ask us to arrange bond length, sometimes stability, sometimes bond dissociation energy, sometimes bond energy. Bond length, bond order, which is inversely proportional to bond length. This is the points, very important, dear students. Next one, fourth point here, bond order which is directly proportional to the stability. The number of bonds more in the between the atoms or molecule, that compound will be more stable. Next one, bond order which is directly proportional to here, bond strength. Next one here, same, bond order which is directly proportional to bond dissociation energy. This is a very important. Single bond is there, and as well as double bond also there, and triple bond also there. Now single bond is there. If you take it this one more, this is also carbon, this is also carbon. If you want to break this, single bond is there, you can easily break the bond because only one bond is there. If you want to take it here double bond, there is two atom bonds are there like this. If you want to break, you have to supply large energy in this one. This is the bond dissociation energy order. Next one here, for example, if you take it here, what about homo and as well as atomic and heteroatomic molecules? Homo atomic molecules, if you take it here, H2 will be, and He2, C2, B2, and N2, O2, Ne2, and so on, etc. These are all molecules which comes under here, homo atomic molecules. Next one, what about here, heteroatomic molecules? Hetero means different atoms. You can take it here. Let me take it here, CO, NO, NO plus, CN, CN minus. Next one here, CN plus. You can take it here different. And so on, etc. This is homo and as well as hetero. Small points I'm going to write here. Now whenever even number of electrons are there, and over here, next one, what about magnetic character here? I am writing here, very important. They will ask which of the following ion or molecule having the paramagnetic or diamagnetic in nature. Then magnetic nature, we know that is one is comes under paramagnetic, second one is comes under here diamagnetic substance. Paramagnetic, generally we have to tell here odd number of electrons are there. It is comes under here paramagnetic substance. Whenever diamagnetic substance here, paired electrons. Paired means here I can write it here even electrons. Even, sorry, all the even electrons which comes under diamagnetic substance, no, very important, giving here exception case in whenever the even electrons are there. I am writing some exceptions is there. Boron and as well as here O2 and S2. These two, these three molecules which comes under generally, even number of electrons, because 5 plus 2, 5 plus 5, 10. Here 10 is there, here 16 is there, here 32 is there. Now here even number of electrons is there, but it doesn't form diamagnetic substance because the number of electrons is present in O2 and as well as S2 here, anti-bonding orbitals. Anti-bonding orbital. That's why it is one unpaired electrons. Here also one unpaired electron, two unpaired. Here also two unpaired electrons. Unpaired electrons is present. That's why here paramagnetic substance I can write here unpaired electrons. If unpaired electrons is there, that's why you can easily calculate here paramagnetic substance. Paired electrons are even diamagnetic, but exception is there B2, O2 and as well as S2. Let me take it one example here, one, and this one how to calculate. Let me start with here H2. Now if we take it this one, now this is the orbitals here. Hydrogen generally we know one, its configuration is 1s1, number of electrons here 2. Now here one more atom also there, that is why 1s1. Now I am writing here, this is one hydrogen, this other hydrogen. I am writing here 1s, here 1s. This is a representation. This is only called as here molecular orbitals. This is sigma 1s, this is called as sigma star 1s. This is bonding, this is anti-bonding orbital. 1s1, 1s1. Now let me filling the electrons in 1s here, 1s1. Here also 1s1 I am filling. 1 plus 1 here, 2. That's why I am filling here according to Hund's rule is following. 2 electrons. I am writing here sigma 1s2. What about here sigma star? 1s0. Now let me apply all this one here. First of all, I am calculating bond order. Bond order is equal to here. First of all, how many NB? NB is equal to 2. Na is equal to 0. Already know NB which is greater than Na. Obviously molecule is, what is the condition here? Nb greater than Na, the molecule is stable. Now half into 2 minus 0, that is equal to 1. How many bonds you are expecting between two hydrogen atoms here? Single bond. Okay, but single bond also, okay, if you want to break, you have to supply large amount of energy, approximately 435.8 kilojoule per mole. Sir, only single bond also, that much amount of energy we have to use. That means, okay, it involves here s orbitals. S orbitals, it is very closer to the nucleus. Okay, well, if you want to remove the electron from that one, okay, we have to supply large amount of energy. That energy called as here, okay, bond dissociation energy of H2 is 435.8 kilojoule per mole. This is, okay, bond order. Next one, everything we know, bond order, which is inversely proportional. Bond order is directly proportional to stability. Okay, bond strength, bond dissociation energy. Okay, obviously we can take it. Okay, next one, let me take it here. One more molecule, you can take it here, O2. Okay, O2, if you take it generally, okay, total number of general oxygen electron configuration 1s2, 2s2, 2p4. Next one, this is one oxygen atom only. I am writing here one more, 1s2, 2s2, 2p4. If you take a total number of electrons here, 8 plus 8, 16 electrons. Okay, don't forget, okay, well, 16 electrons, that is even. No sir, immediately I have to go for mark for diamagnetic, wrong. Okay, now it is comes under paramagnetic substance because it is an exception case. Okay, now you can write okay, like this also you can take it here. Okay, generally, okay, if 14 electrons is there, general, okay, we have to represent molecular orbital is like this. If now more than 14 electrons is there, we can represent electrons here sigma, okay, 2px and as well as pi 2p pi 2. There is some, okay, energy levels will be, okay, exchanging due to more repulsions. Okay, well, now here 16 electrons are there. Bond order, if you want to calculate here, half into, okay, without drawing the diagram you have to, because in NEET exam or competitive exam, if you want to draw, it will be taking more than 10 minutes. Okay, here Nb is equal to here 10, Na is equal to here 6. Okay sir, how can you know sir? Nb is equal to, okay, 6, 10 here 6. Which, okay, molecular ions which crossing the 14, including 14 also, you can easily take it here. Nb is equal to 10, Na is equal to whatever. You can check it here 16, here 10. Okay, remaining how many electrons here? 16 minus 10, 6. Okay, this is a very important shortcut we have to use. 10 minus 6 is, that is equal to here 2. How many bonds you are expecting between oxygen atoms here? There are double bond here expecting. This is the O2 molecule, bond order is equal to here 2. Sir, what about then? Very important, number of times asking question O2 and as well as here O2 plus and O2 minus and O2 2 minus. What about here? Is any shortcut is there sir? That means here I am going to give the here number of electrons is there and as well as what about here bond order, within fraction of seconds you can calculate. If the, for example, number of electrons I am writing here, next one I am writing here bond order. Okay, you have to follow this one. You never get confused while solving the questions. Okay, here I am writing here 10, 11, 12, 13, 14, 15, 16. Okay, well, here 17, here 18, here 19, here taking 20. Okay, if you understand this one, you can do it. Okay, number of electrons if 10 is there, 11, 12, 13, 14, 15, 16, 17 is there, 17. Next one, if you here 17, here 18, 19, 20. Okay, now bond order I am doing here. Bond order here 1, 1.5, 2.0, okay, here 2.5, here 14 is there, that is 3. Then after 1, 1.5, 0.5 difference from start with 1 and here up to 14, okay, bond order is equal to 3. Then after what you have to do sir? Then you have to write the descending order. Let me write here 2.5. Next one here, it's not visible, I am writing here 2.0. Next one 17 is here. Okay, then 1.5, 1.0, here 0.5 and 0. This is the way we can check it here. 16 electrons are there. What is the bond order? Check it here. There are number of electrons is equal to 16. Bond order is equal to 10. Okay, so 2 or not? Okay. If you take it to 17, what is the bond order here? 1.5. Now what I gave the example here, O2, O2 plus, O2 minus, O2, 2 minus. Now let me take it here, number of valence number of electrons here. Here 16, here 16, okay, plus means minus 1. Okay, here 15, here O2 minus 17, here O2, 2 minus, here 18. Now you can easily calculate the bond order without getting confused. 16, what is the bond order here? 16, 16, 2. Okay, here 2 bond order. Here what is the bond order? 15. 15 means here, we can take it here 2.5. If you take it here 17, bond order is 1.5, 18 bond order 1. They will ask increasing or decreasing order of bond order. Just you can take it here, bond order. If you take it, bond order of this molecule, ions, which is the first bond order here. I am writing the increasing order. Increasing order first, what will come? O2 2 minus, which is less than, then after O2 minus, next O2, then after O2 plus. This is here bond order already 1, 1.5, here 2, here 2.5. This is the bond order. Next one, if you take it here, sir, I want bond length. Bond length means it is inversely proportional. They will ask some questions here. Arrange the following ions into decreasing order of stability. Decreasing order of stability, number of already written, number of bonds which is directly proportional to stability. Number of here bonds, that means bond order directly proportional. This is the answer. Bond length, if you take it here, reverse will come. Bond length. Bond length which is more bond length, less bond order. Next one, bond dissociation energy will be here high. Next one, bond strength. This is the way we have to calculate the molecule, what is the bond order for a particular ions or molecules for anything. But we have to remember only one point, this point, dear students. If you remember this one, you can easily calculate like this. Whatever the N2, N2 plus, N2 2 minus, N2 minus, anything, just you have to note down. That point is very, very important. This very important point which you have to remember. Please note down, dear students.